Okay, so this video is going to be about something called the impulse response, and also how it can help us get outputs to LTI systems. Okay, so first, what is the impulse response? So the impulse response and we're going to denote it h of t, the impulse response h of t of an LTI system. Okay, well, what does it sound like? The impulse response, it's the response of the system to an impulse function, to a delta function. Okay, the impulse response of an LTI system is the output, the response, when delta of t, an impulse function, delta function, is the input. Okay, that's it. Okay, so in a picture, I put delta of t into an LTI system, and what comes out is the impulse response, h of t. Okay? So we're kind of hitting our system with this impulse, kind of like this lightning bolt, and the system's going to do something from that input. And that something that it does, that output it produces, is the impulse response h of t. Okay, and it's kind of amazing, but believe it or not, it turns out that knowing the impulse response h of t is actually enough to determine the output y of t for any input x of t. It's pretty amazing. If you tell me this one function, this impulse response for an LTI system, I can tell you the output to any input x of t you give me. Okay? It's pretty crazy. It's very useful. And in this video, we are going to see exactly how to do that. How can you get the output y of t for any input x of t, knowing just the impulse response? Okay, so here's why. All right, so gonna do a little derivation here. So first, let's pick a small delta that's positive and consider a shifted rectangle of width delta. Okay, so what does that look like? Something like this. I'll just put it over here. Okay, and let's say this rectangle has height 1. Okay, I'll put it over here, height 1, and the width is delta, and we're going to locate it here at n times delta. Okay, so you can maybe have a prediction of where this is going. Okay, but this is a shifted rectangle of width delta, height 1, and I've put it on the location n times delta. And let's try and get a formula for this. So this rectangle is what? Well, I'll write it down and then we'll check that it's right. So we have to shift it by some amount and we gotta scale it. Okay, so why is this the correct formula for this rectangle? Well, remember what rect is. Rect is a function where both sides of the rectangle come down at -1/2 and 1/2. So I just have to plug in these 2 points for the left and right edges of this rectangle, okay, to this function and make sure that that makes the argument -1/2 and 1/2, right? Because then that would line up with those 2 sides of the rectangle. So what's this point on the right? Well, it's just n delta, that's halfway in the middle of this rect. And so I have to add half the width to it, plus delta over 2. Okay, so what happens when I let t be n delta plus delta over 2? When I plug that in here, so you can see the n delta cancels, and then I'm left with delta over 2 divided by delta, and that's a half. Good. So rect of a half is where this right side of the rect comes down, and that's exactly what happens for our picture as well. So that lines up, that's good. And then if I plug in the left side, n delta minus delta over 2, same thing. So if this is n delta minus delta over 2, I subtract n delta, so I have minus delta over 2. I divide by delta, I get minus 1/2, and sure enough, rect of minus 1/2 is right where that left side comes down. The same thing for our picture. Okay, so this formula looks good. That is the equation of that rect function. I'll erase all of this. And now we're going to consider an arbitrary input. Now consider an arbitrary input x of t. So I'll just draw something here. Okay, so I don't know, let's say it looks something like that. Okay, and we're going to approximate this function by these rect functions. That was a little wide. Okay, just a picture, you get the idea. Let's draw a few more. Maybe some on this side. Okay, you get the point. Okay, and these are all going to be located at these points, okay, which are all going to be of the form n times delta. They're all going to have with delta. Okay, this is a function of t. This is my x of t. Okay, and we're going to approximate our signal x of t using these rect functions. Okay, so what does this approximation look like? This approximation of x of t is, what is it? So x of t is approximately equal to this sum, okay, of what? Well, what's the area, or I mean, not the area. What we're really doing is approximating x of t by this sequence of rects, okay, these heights. So at any point in time, what's this function going to look like? Well, it's going to be a rect function. And which rect function? Well, it's exactly the one we wrote above. T shifted by n delta and scaled by delta. Okay, but what are these heights? Well, we're going to take the heights to be the midpoint of where those rects are centered. So x of n delta, right? That's that point right there. That's x evaluated at this point n delta, and that is going to be how much we scale our rect function by. This is x of n delta. Okay. And now I'm just going to introduce another term here. So I'm going to divide and multiply by delta and shift some stuff around. So I'm going to have 1 over delta. I'm going to put that in. Then I'll have rect of t minus n delta over delta. And then I'll have x of n delta and then times delta to cancel that 1 over delta. Okay, now why did I do that? Well, now this function right here, 1 over delta times that rect function, what does that look like? Well, that looks like a rect function, okay, that has width delta, okay, and height 1 over delta. So it's got area 1. These are just like the rect functions we saw in the last video that were getting closer and closer as delta, in that case t naught, got smaller. Okay, so that's exactly what's happening here. So this gets closer to delta of t minus n big delta as big delta goes to 0. Okay, because these are just rects that are tall and skinny, and they get taller and skinnier as delta gets smaller, and this is exactly what we defined the delta function as in the last video. Okay, so that's what's happening there. And now let's try and figure out what this function looks like when you put it into an LTI system. So let's look first at what delta of t minus n times big delta looks like. So from the TI property of the LTI system, okay, we know that delta of t goes in and we get the impulse response h of t out. Okay, so what happens when I shift my input by n delta? Well, by time invariance, I should get the same output I got before, h of t, just shifted by the same amount. Okay, so I should get h of t minus n delta out. Okay, so we're going to use that now. Okay, so if this term is getting closer and closer to delta of t minus n delta, then on the output side, okay, when I put all of these terms through the LTI system, okay, what I should be getting is a bunch of terms that look like h of t minus n delta. And then by linearity, right, all we're doing is adding this up, adding all these signals up, multiplied by these scaling factors. Okay, so that's all under the property of linearity. Our output, I'll write it down. We can see what our output should be using the linearity property. So by linearity of the LTI system, oops, the output approaches what? I'll run through it one more time. Okay, so y of t going to approach what? Well, all these functions are getting closer and closer to delta of t minus n delta, big delta. We just saw that when I put that through the LTI system, I got a bunch of terms that look like that. So I'll write those in, h of t minus n times big delta. And then all I'm doing to those terms is scaling them and summing them up, right? And so by linearity, I should get just all of these outputs scaled and summed in the same way. So times x of n big delta times delta. Okay, and what does this start to look like as delta goes to 0? Well, this is that Riemann sum definition of integrals again. We're going to get an integral from negative infinity to infinity. And then whenever I see n delta, I have to use a new variable. Turns out that people tend to use tau, actually, in this context. So that's a Greek tau, x of tau. And then this delta here turns into a d tau. Okay, and this is the Riemann sum definition of integrals. Okay, so that's what we get. So let me just say in summary, if the input to an LTI system is some function x of t, then the output is what we just found. Y of t going to be this integral of h of t minus this integration variable tau times x of tau d tau. Okay, so that is the output of this integral. So if you tell me the impulse response h of t and you tell me your input x of t, I perform this integral and I get your output y of t. So that's what we said at the beginning. If you know the impulse response h of t of an LTI system, then you can find the output to any input. And here's how you do it. Use this integral. Okay. And we'll give the name to this integral in a second, but I just also want to write alternatively, and this is just using a change of variables. You can try this at home by a change of variables. Okay, you can just let this t minus tau be some new variable and see what you get. And here's what you do get. You get an alternate form for the output. Okay, it's going to look very similar. All I'm going to do is switch the t minus tau and the tau in this expression. So we're going to get h of tau, x of t minus tau, d tau. Okay, so these two things give you the exact same output. These are just two alternate forms of the same answer, y of t. Okay, it's two ways to get the answer. Okay, sometimes, depending on which of these functions is more complicated, x or h, the impulse response of your input, maybe it's easier to put t minus tau into one or the other. Okay, but they'll get you the exact same answer every single time. They're exactly equal. And these are called, what are these called? Are called convolution integrals. Convolution integrals. Okay, so we're going to be dealing a lot more with convolution later in the class. This is our first little introduction into convolution integrals. We're not going to do much with it now. It's going to come later. Okay, but this is what you get for the output to LTI systems. You tell me the impulse response h of t. You tell me your input x of t. I perform this convolution integral operation on them, and you get your output y of t. It's pretty amazing. Okay, so the impulse response completely characterizes the LTI system because you can get the output from any input given just that impulse response. Okay, so that's it for this video. I will see you in the next one.